Welcome to the 1995 ISDC. We're running a little bit late. We're hoping to be able to catch up. Dr. Robert Zubrin is going to be our next presenter, and he is currently a staff engineer at Martin Marietta Astronautics. He holds a master's degree in aeronautics and astronautics and a doctorate in nuclear engineering. He's the inventor of several unique concepts for space propulsion and exploration, the author of over 90 published technical and non-technical papers in the field, and is a member of Martin Marietta's elite scenario development team charged with developing broad new strategies for space exploration. Dr. Zubrin will be talking about propellants on Mars. Please welcome Dr. Robert Zubrin.
What I want to talk about is a hardware demonstration project that we did at Martin Marietta, or Lockheed Martin, to show that you can make rocket fuel on Mars out of Martian air. And as I pointed out on previous talks, and I'll discuss again somewhat in my talk tomorrow on colonizing Mars, if you can make your rocket fuel on Mars, you're an awful lot of the way towards getting humans to Mars, because it means that you don't have to haul it out with you. And the rocket fuel to come back is most of what you have to send to Mars. If you can make your fuel to come home living off the land, you can reduce the mass of the mission by a factor of 3 and reduce the cost of the mission by even more. So, but what we did here was we decided we would demonstrate that this in fact could be done using a practical process. And we actually built our machine to be full scale, not for an actual manned mission, but for a Mars sample return mission, which is also a mission of great interest to the scientific community, and which would be a demonstration for doing it on an even larger scale than the Humans to Mars program. So the process that this is all based on is called the Sabatier electrolysis, or SE process. And the essence of how it works is shown in this diagram. Okay? You take a small amount of hydrogen with you to Mars, okay? And then you suck in the Martian air, which is carbon dioxide, 95%. And these two will react in what's called the Sabatier reactor, named after a chemist who lived in the 1890s, who did a lot of work with this. CO2 and hydrogen will react to produce methane, natural gas, excellent rocket fuel, okay? And water. The methane you tap off and put that in your fuel tank. The water you take and you electrolyze it, split it into hydrogen and oxygen. The oxygen that comes off is, of course, your oxidizer to burn the rocket fuel, and the hydrogen is recycled to make more methane and water, and so forth and so on. And if you do this set of reactions alone, you'll turn every ton of hydrogen brought to Mars will turn into 12 tons of methane oxygen bipropellant on the surface of Mars. It's a leverage of 12 to 1, it's excellent, and it ends up with a specific impulse of 380 seconds. And there are various tricks you can do to add on to this system that can get the leverage up to more like 18 to 1. If you get around to designing it, your diagram starts to get a little more complicated, and it starts looking like this. We built the Sabatier reactor from scratch, and it's shown here. This is a Sabatier reactor. This is 14 inches long, and 2 inches in diameter, and it's about a little less than half filled with a ruthenium on alumina catalyst. And these are nichrome heaters strapped around it, which you would heat it to around 300 centigrade to get it started. And then you input the gases, and at 300 centigrade they react well, and they produce heat. Enough heat, in fact, to keep it pretty warm so that you can greatly turn down the power required to run it. Because we were on such a short timeline, we over-designed this system. As it turned out, we over-designed it by at least a factor of 10 in required volume. It's much bigger than it needs to be, but we're not going to have time to rebuild it if we had gone too small. So that's why it's as big as it is. And unfortunately, while that did guarantee that it worked quite well, it made it so big that it had a large heat leak, so that we had to keep sub-power in the heaters all during operation, around 50 watts, even after it was up and running, because it was so large. In our next generation machine, not the one I'm going to show you, but the one we're building now, we're going to make this about the size of a ballpoint pen. That's the Sabatier reactor that you see there. is, as I said, at least 10 times the size we require for our production rate. So it could be a lot smaller, or correspondingly, it could produce much more propellant than we're actually making. This thing, though, is the electrolyzer. This is actually originally a Hamilton standard electrolyzer, which then later in life was put in a Packard instrument hydrogen laboratory source, only to be untimely ripped out of it by our technicians and put here. This thing weighs 3 kilograms wet, that is when filled with water. The Sabatier reactor you see there weighs around 10 kilograms, but as I say, I think it could be reduced to around 1. So this weighs 3 kilograms, and this uses 120 watts of power to produce the amount of propellant we're making. And that's a number you're going to have a hard time getting away from, because it's about 85% efficient. This is a small, elegant, and extremely sophisticated device. It's the product of hundreds of millions of dollars of your tax money at work for the Navy nuclear submarine program. And it can withstand very large shocks, including depth charging. So it ought to be able to take a mission to Mars. This then is the whole machine, phase 1 machine you see here in the early stage of checkout. And you can see as I said, the CO2 would come in here, the hydrogen would come in here. They mix in here to make methane and water. The water is condensed out in this condenser loop here and accumulates in this water bottle. The methane would be tapped off to be sampled by a gas mass spectrometer or chromatography. We had both techniques. And the water would then go through here into the electrolyzer to be split into hydrogen and oxygen. The oxygen could be tapped off and sampled, and then the hydrogen would be recycled back into it. And so that is the core chemical system for a Mars propellant maker.